Hello, this is part 3 in our electrical circuits tutorial series, and we will be discussing series circuit rules and series circuits in this tutorial. So we have a set of rules that we have to abide by for a series circuit. If we violate any of these rules, the circuit will not work. Even if we have a defective component in the circuit, the rules are still going to apply. The difference is we'll have changed values to the other components in the circuit. Rule 5 down there, the power rule, the sum of the power dissipated by individual components equals the total power. That applies to all circuits, not just series circuits, so it'll apply to a parallel circuit and also to a series parallel circuit, which we'll discuss in later parts of this tutorial. Now, a good example of a series circuit would be Christmas tree lights. If we have those Christmas tree lights we put up and none of them work, and we go out and pull out one bulb at a time, replacing it with a known good bulb until the entire strand comes on, that would be a series circuit. There's only one path for the current to flow, so if one component opens in that circuit, the entire circuit fails. If you've had a set of Christmas tree lights that a bulb goes out and half of your lights go out, is simply because you have two series strings in that strand of Christmas tree lights. This is a schematic, a wiring schematic, our map of how to wire something. And a few little things about it. This symbol right here, that is the battery symbol. It is a cell symbol actually, which is the smallest component of a battery. We use the cell rather than linking multiple cells together just to save some real estate. The long bar on a cell is always the positive, the short bar is always the negative. Up here at the top we have that zigzag line. That is a schematic symbol for a resistor. A resistor is a load. This would be R sub 1, this one would be R sub 2, this one would be R sub 3. Now, even if they're not numbered, you can number them like that. Whenever I'm using subscripts, like the R sub 1, that subscript is just an identifier so that we know what component we're talking about. That way when we start getting good and bad components in there, we know what's what. If I use a subscript of T, that's meaning we're talking about circuit totals. Now, to make this schematic a little bit less congested and less confusing, I've taken the control device out of the circuit. The control device would be a switch, a relay, a solenoid, a transistor, a PLC, something to that nature that controls the circuit to energize and de-energize the circuit. Now, to be able to tell if it's a series circuit or what kind of circuit it is, we're going to trace it, and as stated in part 1, I go by the electron flow theory. And so right now we only have one path for the current to flow. We go through our first load, we still only have one path. We go through our second load, we're still at one path. Through our third load, we're still at one path. Full circle back to our cell or our battery, our source, our power source. And so, by definition, since there's only one path for the current to flow, this is a series circuit. We're going to be using ear and pie thumb wheels that we discussed in part 2. And the series circuit rules we just saw to calculate the expected values that we should expect to see. Now, when we're doing our calculations, we use the values that the component is supposed to have. That way we have a good baseline so that when we do the calculations, we take that with us when we go to the live circuit and we start taking live measurements on that circuit and comparing them to what we calculated they should be. We use the math as, am I close? Yes. I don't have a problem with my part of the circuit. Go look somewhere else. Am I close? No, you're out of the ballpark. I have an issue with my part of the circuit. You need to look at me a little closer. That's what we use the math for. So our current rule for a series circuit, that the current remains constant through all components in the circuit, we can say it as I sub t is equal to I sub 1 is equal to I sub 2 is equal to I sub 3, and in this case it would be 2 amps. Our resistance rule, the sum of the individual resistances always equals the total resistance. We could say R sub t is equal to R sub 1 plus R sub 2 plus R sub 3, which would be equal to R sub 1 of 20 ohms plus R sub 2 of 10 ohms plus R sub 3 of 30 ohms equals 60 ohms total. Our voltage rule for series circuit, the sum of the individual voltage drops always equals the total voltage. So we could say E sub t is equal to E sub 1 plus E sub 2 plus E sub 3, which would be equal to E sub 1 of 40 volts plus E sub 2 of 20 volts plus E sub 3 of 60 volts equaling 120 volts total. We could use Kirchhoff's series circuit voltage rule also, which simply states we take the total voltage and subtract the individual voltage drops and it will equal 0. It says the same thing, it just says it a little bit differently. Our power rule now here, remember rule 5, not only applies to series circuit, but it also applies to parallel and series parallel. It will always hold true. The sum of the individual, of the power dissipated by the individual components will always equal the total power. So P sub t is equal to P sub 1 plus P sub 2 plus P sub 3 would be equal to P sub 1 of 80 watts plus P sub 2 of 40 watts plus P sub 3 of 120 watts equals 240 watts. We can use the pi wheel, and our power is equal to our current times our voltage. So we take our total current of 2 amps and we can multiply it by our total voltage of 120 volts and get that same 240 watts. Here's the circuit enlarged so you can see the values with each component. Over by the source will always be where we put our totals on this. And this concludes part 3 of our tutorial series. Thank you.